Hello and welcome to Fire Dynamics in Forensic Investigations. I'm your adjunct instructor for this course, Jamie Lord. If you have any questions or you need to get a hold of me, you can always reach me at jamie.lord@osu.edu, or you can post any questions you might have on the D2L course website on the discussion boards, and that way everybody can benefit from any questions or discussions that we might have. Our first lecture this week will be an introduction to fire dynamics, really just to get things started, talk a little bit about what fire dynamics is, and really how it can be useful to us as fire investigators before we go into a little bit more of the housekeeping aspects of the course. So we're going to start out with a little bit of an intro, and then I'd like to take a little time on this first week just to go over some sample problems as to what types of benefits we can get from fire dynamics in our fire investigations. So the first one will be a very simple room flashover calculation, and that's something that could be useful in a lot of scenes, and you could do it really while standing right at a scene quite quickly and get some useful information out of it. The second is a more complicated example from an apartment complex fire, and that one's not something I would expect you to do while you're working a scene, or even without having several years of experience in fire dynamics and perhaps some testing and computer modeling. But I wanted to throw it out there as an example of the sort of extreme end of what can be done using science and fire dynamics to support a fire investigation case. So when we've gone through those, I'm just going to end this lecture with a little bit of housekeeping. We'll go over the expectations for the bi-weekly problem assignments, the discussion board that will be given also every other week, the weekly online quizzes, as well as some discussion about the term paper and the final exam. So what is fire dynamics? If we go to 921, which I would encourage everyone to be familiar with, if you don't have a copy of NFP 921, be definitely in your best interest as a fire investigator to get one. But if we go to the new version, it's going to define fire dynamics as the detailed study of how chemistry, fire science, and the engineering disciplines of fluid mechanics and heat transfer interact to influence fire behavior. And that is a good definition, and there's a lot of different components to that we're going to be looking at throughout this course. To me, sort of a less wordy definition, if you will, of fire dynamics, we look at this movie here, and what this is what we call a flashover cell, and you notice that I'm playing the movie backwards. And I do this because if you look at this right now, let me pause this for a second, this fire is the best case fire scene that you might ever come across as a fire investigator. So this is a scenario where you get there, the fire department hasn't even knocked it down quite yet. It's fully involved. It's this room of flame essentially, and we're supposed to figure out as a fire investigator, where did this fire start? In reality, we're not even going to have quite this much information most of the time. We're likely to get there, and there'll be a black hole and maybe no walls left, not much to look at. So let's look at this though, and picture, if you will, we're being asked as fire investigators to create this movie in our head, to work backwards from a fully involved fire, where the fire department gets there, to the origin and hopefully the cause of this fire. So to do that, we need to understand how the fire is moving around. How does the energy get from one place to another? What are the dynamics of this scenario here? So really the whole point of this fire dynamics course is to, if you will, give you the scientific background that you can create these movies in your head. So you can visualize what's going on in these fire scenes, but also to use a little bit of math and science to back that up and support how you got to your answers. So just picture this as you're going through. This is sort of why we're interested in fire dynamics, because we're being asked to do this every day on our fire scenes. So when we look at a fire, I think it's worth stepping back even a little bit before the fire, thinking of it as energy, essentially. So everything in the universe has got a whole bunch of energy locked up inside of it. And the same is true with everything in our houses, our buildings, anything in an area we might be investigating in a fire. All those objects are chock full of energy. And really what we're doing as a fire investigator is trying to figure out what was there, how much energy was inside, and how that energy got unlocked during the fire. So how did it move around? What was the level of energy that we were seeing? And that's where we get our patterns forming from. That's what all our visual clues eventually are coming from, is the energy that started out in all of those materials. So when we look at energy, let's look at a very common example here. Think about a Snickers bar. It's easy for us to figure out the energy in a Snickers bar because some laboratory somewhere has already done that test for us, and they've been nice enough to label it for us. So we know that in one Snickers bar, there's about 250 calories. Now I'm going to start introducing a little bit of a graph into our Snickers bar here, because as we go through the class, it's going to be very helpful a number of times to show things in graphical format. And once you get used to looking at them, it's going to, I think, help you take in a lot of information really quickly, which is why we engineers and scientists like to use so many graphs all the time. So picture this one. We have our Snickers bar, and if we look at the left side, where I've got my arrow here, I've just labeled that. That's the energy in the Snickers bar. So that's the number of calories that are in there. So if I were to draw a box around this Snickers bar, the inside of that box would equal 250 calories, say, the total amount of energy. If I now add an x-axis, so this bottom bar, onto my graph, that adds a time component to the amount of energy in this Snickers bar. And the way I'm phrasing it here is how quickly we can get that energy out. So if we picture, like I said before, the inside of the box is still 250 calories. If we have, say, a very greedy person who decides to eat this Snickers bar over the course of 1 second, then he's going to release, if you will, 250 calories from that Snickers bar over the course of the 1 second shown down here on the bottom. So I would say in this case that the energy release rate from eating the Snickers bar in one big bite is 250 calories per second. So let's just take the Snickers bar out and look at this graph momentarily. We have our energy release rate still, and the time on the bottom. I haven't changed any of the graph, I just removed the picture. But the important things here are the peak here, the top. This is our energy release rate, and we're releasing all 250 calories in that Snickers bar over 1 second. The area inside the curve here is still the total 250 calories that's inside that Snickers bar. And bear with me, we're going to relate this to fire pretty soon, but it's a very important concept for us to get down early on. Let's say that I'm a little less greedy when I eat my Snickers bar, and now I'm taking 2 bites, or 2 seconds, to release all the energy from this Snickers. Okay? So the area inside our little box here is still the 250 total calories of a Snickers bar. So the total energy release is still 250. But because we're doing it over a long period of time, 2 seconds, now we've cut our energy release rate from 250 calories in 1 second to a level of 125 calories per second over 2 seconds. So we've slowed down the rate at which we're releasing the energy from this Snickers bar. But all the components of the graph are still the same as they were before. When we talk about fire, we're still just talking about energy. And in this case, the specific form of energy that we're talking about is heat. And heat is just a form of energy characterized by vibration of molecules, and it's capable of initiating and supporting chemical changes and changes of state. So if we swap from our Snickers bar 250 calories to an actual fire releasing some heat from something, let's take this chair for example. So a chair, typical wingback chair you might find in somebody's house, which is probably polyurethane foam cushions with some sort of cotton fabric covering. In this case, nobody has been kind enough to label the calorie content of our chair for us, so we're going to have to go ahead and get at that a different way. We do that in the laboratory through a couple different ways we can do it, but what we're going to show you today in one video, and probably be seeing most of the time in our references, is an instrument called a calorimeter, and we'll get into a little bit later how that actually works. But let's equate this chair to our Snickers bar, if you will. So here we have a graph, and it's got all the same components that we had before. We've got the energy released on the side. In this case, we're talking about heat, so let's call that the heat release rate. And we've got the time down on the bottom, just like we had before. Everything inside this blue line, just like before, is the amount of heat that is going to be released when we burn this chair. It's going to be easier to think of that in metric terms, because that's what most of our equations are in. So instead of calories, all we're doing is calling it kilojoules. It's the same type of measurement, it's just a different label for it, a different unit. Up here on the top, we've got these spiky lines here, and that's our heat release rate. So that's the rate at which the energy is being released from this chair as we burn it. And that's in kilojoules per second, which we would also refer to most of the time as kilowatts. So that's a similar term you've heard before. That's what we measure a light bulb in, and the amount of power that we're using is the energy over time that we're using, getting billed on our power bill, using in our light bulb. And also, in fire terms, the amount of energy over time that's being released from a piece of furniture or any item that's being used as fuel during a fire. So, in this graph, we've got our peak heat release rate is the highest part. The sort of general heat release rate over time is all the different pieces of this blue line. And everything underneath, all the inside area, is just the total amount of heat, or the total amount of energy that's being released as we burn this chair. Now let's look at a couple different phases of this line, if we can. See the beginning part, it's this very small little blip here, where we're going from 0 seconds to maybe, I'll call that 40 seconds or so. And you see there's almost no raise in the level of heat release rate, and that's because that's what we call the ignition phase. And picture that, this is igniting maybe some newspaper on the chair, what have you, with a small flame. And it's going to take a little while before anything catches hold, and the fire really starts to grow at all. So that's the ignition portion, right here, that little line. As we get a little more established, our fire gets bigger, we hit this very steep growth rate here. This is the growth portion of the curve, we call it. And that's going very quickly because as the fire grows, starts to heat up, we're getting a lot of heat transfer from the flames into the different parts of the chair. And because it's preheating everything, they start to burn more quickly. And that in turn is going to cause the flames to grow, going to cause more heating, and form this sort of feedback loop that causes our fire to grow very quickly. And that's the growth phase of the curve here. And you see these little peaks here. We call that the peak heat release rate portion of this curve. And that's sort of the maximum burning that we're going to get from this fire. And there's a few reasons we might reach a maximum. We're either at a point where we're running out of fuel, we're at a point where there's no longer enough air or oxygen to sustain the fire, or it may start to reduce a little bit if we start spraying water on it, if the fire department comes in and puts the fire out. So I'll tell you, in this case, we're burning this chair out in the open, so it's really It's not ventilation limited. There's plenty of oxygen available in the ambient air. So what we're seeing in these peaks here is sort of different fuel packages getting involved at different times. So maybe we have the bottom cushion being ignited and burning first. As that starts to run out a little and dip, maybe at some point we've got the back cushion to ignite a little better. That burns out a little and dips, and then we get another peak as maybe we've got now two cushions or a cushion and an arm going at the same time together. And then when it tapers off here, it's going to generally look like this here if we started running out of fuel, or often it'll look like that too if you sprayed some water on it and did some suppression. So those are all the pieces of the heat release rate curve, and we're going to see that over and over again, and I'll show you very quickly here why we care about heat release rate and why that's one of the fundamental things to look at in fire dynamics. If you see this capital Q with a dot over it, the Q dot, this is just the symbol for the heat release rate. So the amount of energy being released over time, the heat release rate, Q dot. Those are all the same thing. You'll see them often. Every time you see an equation with a Q dot, you're going to know that it's looking for this heat release rate. So let's now just look at a video of this chair. It's sort of a smallish wingback chair. This one is in a laboratory under a calorimeter hood. Just a quick version of what that hood is doing. It's measuring the amount of oxygen in the air that is being pulled up through this exhaust hood. So as the fire burns, it's depleting the oxygen that's in the air that we're pulling through this hood. And what we can do is then take that information, do some calculations with it, and back out what the energy being released over time is from this fire based on how much oxygen is being consumed. So don't worry for now exactly where that comes from, but take a look at the numbers that you see next to the HRR, which is our abbreviation for heat release rate. So right now we see 40, 44 kilowatts and rising quickly, and that's coming into the growth phase of our fire. If you see a number in a book somewhere that says you've got a fire 50 to 100 kilowatts, so you picture a fire this size, and that might be consistent with a sort of small plastic trash can that's full of papers on fire, something like that. Although we're quickly now at this point getting to a little bit bigger fire than that would be. It's heading towards a couple hundred kilowatts. Something interesting to note while we watch this, look on the bottom underneath the chair. You see a lot of dripping and drop down from there. That's from the polyurethane foam that's inside. It's just melting as the chair burns, and it drops down there. And what you find in a lot of fires, it looks like a pool fire underneath, which back in the day would have been maybe confused for signs of an accelerant being used. But now we know you really just get that from most pieces of furniture. Okay, so look up here. While I was chatting about the pool fire, we peaked at somewhere over 600 kilowatts from this chair fire. And we can see it's already starting to come down, not because it's out of air, not because we're putting the fire out, but because we started to consume a large portion of this chair. It's basically running out of fuel, and it's going to slowly taper off until the chair is gone. But picture a fire this size, so that's probably 4 or 5 feet tall, 2 or 3 feet wide, gives you this 400 or 500 kilowatts. If you notice now, it's ramping back up again. That's what I mentioned before. We've now gotten sort of other parts of the fuel package involved. So maybe a pillow that was not burning before is now caught, and we're burning a couple pillows and forming another one of those peaks. And it'll go up and down like this if we leave it as it spreads to different parts of the chair and gets different fuel packages involved. If you picture on a larger scale, if we put this in a room and we have lots of different furniture items, other types of fuel around, then you're going to see that same thing. The fire is going to grow, and it might start to taper off as it consumes one piece of fuel, but when it spreads to the next, it's going to then add on and start peaking up a little further again. And then in a compartment, as we spread to more and more items, that's when we quickly get a much bigger fire, which typically is going to be limited only then by the amount of air that's available. So our peak here now, we're up to over 650 kilowatts. But we've quickly started consuming most of the padding on that chair, so it's going to start coming down as all that fuel is consumed. So just a few examples of some numbers you might see for heat release rates of different types of fire. And keep in mind these are all sort of orders of magnitude, just approximate numbers. And there's going to be a lot of variation from one item to the next. But a candle, we're looking at about 50 to 70 watts. You notice a watt, there's 1,000 watts in a kilowatt, so a watt is pretty small in terms of fire. And that's typically what you get energy-wise off of a light bulb. If we go towards a little bit bigger fire, in the upper right we have this small pan fire. I don't remember the exact size of this, but picture that's about 1 foot in diameter probably, and it's probably got some gasoline or some similar fuel in there. But if you see a fire about that size, say about the size of a trash can, then we're looking at 100 kilowatts, give or take. Go to the bottom left. Now we're looking at a sofa that's burning, and we've got probably less than half of that sofa on fire at the moment, and that's probably close to 1,000 kilowatts, which we could also say is 1 megawatt. Right, 1,000 kilowatts equals 1 megawatt. Just because it gets a little easier on the really large fires to drop some of those zeros off. But a sofa, I would say either a small sofa that's fully burning or a larger sofa that's only partly on fire is about 1 megawatt. This little white sofa here from IKEA, if we got that whole thing burning, it's probably closer to 2 or even a little bit more megawatts when that's going at its peak. Now down in the bottom right, we've got a much bigger fire. So this is, I believe, a heptane spray burner fire. Those flames are probably about 35 feet tall. There's a couple jets going on there, and that fire is about 10,000 kilowatts, or approximately 10 megawatts in size. So when we start talking about 10 megawatts, that's going to be a large fully involved room, maybe a couple rooms on fire, or something like a couple of vehicles, or a bus or something of that size might give us a 10 megawatt fire. So, why do we care about this heat release rate thing? So why do we care about Q dot? And we're going to be using this over and over throughout the course, which is why I wanted to start things off with it right at the beginning here. And as we go through the next weeks, I think you'll develop a better understanding of why it's important. But the big thing we're going to use it for often is some of our calculations that we're going to do in this class. When we're looking at things like flame heights, when we look at when flashover might occur, and a lot of different other things that we might be looking at, then the first thing we're going to try to track down is the heat release rate of the fire. So this video here shows a rack of bags of potato chips. And what's kind of neat about this example, back to our Snickers and our calories, if you will, if I took the calorie information from these bags of chips, converted those into some metric number, and was able to combine them together the right way, I could actually get a good idea of the total amount of energy that's locked up inside all these chips, inside the bags. If I have that, I can predict something to find out what the peak heat release rate might be. And what's useful with that, then I can plug it into some calculations and we can start predicting maybe what the flame height might be or when a room might flash over. So in this case, say I was interested in the height of the flames above the rack of potato chips, it might give me some information about when it could have been seen in a video camera or when it might have spread through an opening to the floor upstairs or something along those lines. This is an interesting fire too here. You wouldn't maybe think that some bags of potato chips will make a really big fire, but if you think about how fattening they are, right? How bad for us potato chips are. There's a lot of calories locked up inside there. That's just energy. And when we release it in the form of heat, you get a pretty impressive fire actually. I'll be showing you as many videos of actual fires as I can throughout this course. So it really does, I think, help a lot to just see how different things burn. Be able to almost create a movie in your head of how you would expect things to happen. Hopefully I'll be also giving you the skills to back that up with some research, some references. You'll be able to do some calculations to estimate where things might be going in a fire or how they got to where they did. And we'll show as many of these as we can. And as we go through, if you have questions about any of these or there's something you've been wondering about how it burns, how it might behave, then I'd encourage you to go ahead and post something on the discussion board. We can talk through what people have seen, and if I have any test data or other videos of that topic, then I can add those as well. Before we move on to our two examples that we're going to talk about this week, I want to introduce this concept of what we call flashover, which you will come across again and again in fire investigation. So I'm going to start playing this video while I speak over it a little bit. We call this a flashover cell. You might have seen them before in some demonstrations. What they are is it's basically a three-sided room that we've set up with some lovely, in this case, 1970s looking furniture. This one has some wood paneling along the back wall, and we've ignited a trailer of gasoline leading to a waste basket full of paper. But the purpose of the flashover cell is to demonstrate this phenomenon of flashover. And what that is essentially when we've involved all the fuel packages in a room, everything's burning at the same time, so that we've now transitioned from a fuel-driven fire that's limited only by the amount of combustibles available to a ventilation-limited fire that now needs to move outside the original compartment in order to get the air that it needs to feed the fire. So look at where the fire is right now. We see it's very quickly because of the accelerant getting up so that the flames are coming across the ceiling inside. And that's the part at which you get a lot of heat radiating down. You're preheating a lot of the fuels below, and the fire growth really starts to accelerate quite a bit at that point. So if you see a lot of the surfaces here are off-gassing a bit. You see the solid fuel is pyrolyzing. It's basically being turned into vapor by the heat. And those vapors are what are actually burning inside the cell. So I would say right about now, as things are all bursting into flame, right when the carpet goes, that's approximately what you would refer to as flashover. The reason we really care whether a compartment is flashed over or not for a fire investigation is because of what I mentioned. This is when we move from a fuel limited fire to a ventilation limited fire. And what that means to us is we move from a point where the burning is happening perhaps on the fuel package that was first ignited to a point when really the burning is happening now wherever air and oxygen are available to the fire. And what this means is the longer we burn post flashover, so the longer we burn in this ventilation limited condition, the more chance we're going to have to develop interesting patterns that really have nothing to do with where the fire actually started. So let's look at our first example. And this is a simple one that you could do quite easily on one of your fire scenes to get some useful information. I've had a couple similar cases in the past where this was useful. So in this example, we're looking at a small room. We've got a 10 foot by 12 foot room, and let's say it has an 8 foot tall ceiling and a single 2 foot wide door down on this side, which is a little narrow for the door, but I happen to have a test that shows a door like this, so we're going to use that. For this scenario, the only fuel in the room is going to be this wingback chair that's tucked up into the corner of the room. So what we'd like to find out in this case, given just this chair in the corner of the room, is that enough fuel to drive the room to flashover? So in other words, if we were working a scene, digging out a fire, and we come across a room with essentially nothing inside other than this chair, but we have a lot of damage and patterns that indicate to us that flashover has occurred, does that mean we could have got there just through igniting this chair, whether it be accidental or incendiary or something, or would we have had to add some more fuel to this room? So did somebody have to pour some gasoline? Was there some other fuel that we're not seeing because it's completely burned away? So what can we do to figure that out? And this is where some of our simple calculations are going to start coming in. So I'm going to bring in a little spreadsheet here. And let's look at this. And it looks maybe intimidating if you haven't used Excel a lot before. It's not required for this class that you use it, but I will say that it will probably make your life much easier both for this class and in the long run. So what I'm going to do for you as we go through these exercises is week by week I'm going to add to this spreadsheet different calculations that'll be useful for a fire scene investigation. And we're going to learn how to use the sheet, and we're going to learn about the calculations that are in there. So what you can do is take away at the end of the day is a spreadsheet that will allow you to quickly do a lot of calculations. So you don't have to be incredibly good at math. It helps, certainly in fire dynamics, but this is not a math class designed to test your math skills. So I'm going to try to provide us with tools that'll help, get these calculations done in a way that is easiest for everyone, takes advantage of some technology here. So just briefly looking at this spreadsheet, you'll see a bunch of different colors here, and the way I'm going to color code these for you, if you see green, then those are the cells where we're going to want to put some value in from our scene. So in this case, if we're looking at the flashover room, then we need to know things like the dimensions of the room and perhaps the thickness of the wall lining material and that sort of thing. If you see a blue cell like this one here in C9, that's going to be a drop-down box that we can choose something from. So if we had a concrete lined wall, we might choose concrete, and maybe we would change the interior lining thickness to something like 8 inches for a concrete block. For this example, let's go ahead and use gypsum board, and let's pretend that we have 1/2 inch gypsum in there. Where you see the gray cells, these are cells where calculations are being performed. And you don't want to touch those, essentially. You can go in there and play with them if you'd like to, but the spreadsheet's going to calculate those automatically. If you click on one, say we click on cell C12, this AV, which I haven't written out for you, but that's the area of the vent in this case. So if you look in this box up here, we can see that the area of our vent is equal to cell F6 times F7. And if we look at what those are, we see that cell F6 is where I've converted my vent width to metric. Cell F7, I've converted my vent height to metric. So we're just multiplying those together. So a side note, while we're here, I'm starting my sheet in English units because honestly, when we're working a fire scene, that's what we're going to measure. That's what our buildings are built in. So I tend to measure things in feet and inches most of the time. But most of our calculations use metric because that's what all the tests were done. That's what they were derived in. So we're going to wind up converting things to meters a lot. So if you see this little sidebar, conversion to metric, that's what that's all about. So in this case, what I would like to do, looking back at our room, I want to know, is this chair enough to cause this room to flash over? Now, flashover is going to be a function of my fire size from this chair, and it's also going to be a function of how much ventilation is available to this room. In this case, just the single door. In this case, this one is a man door. We'll say it's 2 feet wide by 6 feet tall. So I want to know what's the Q dot, if you will, the heat release rate of this chair that is sufficient to cause flashover of the room. So let's go back to the spreadsheet here. And down here, there's actually a number of ways that we have of doing this. Several different calculations that will give us different answers to the same problem, if you will. And the reason for this is they're based off different sets of test data. Maybe some of them are more appropriate to different size rooms than other, or different scenarios than the one we're looking at. So in this case, I've given you 3 here. We've got this method of McCaffrey, Quinteri, and Harkleroad. We've got a method by Bobrowskis, and we've got one by Thomas. And you see, I've provided all the references here. What I will do, when I put these in here, I'm going to upload those references to a folder on the course website. So you'll be able to go and poke through those if you want. If you want to see why you might use one calculation over another, it's a good idea to look there. I also put this here to show you, as you're doing calculations for your homework assignments, as you're doing origin cause reports for work down the road, it's really going to benefit you to provide references to all your calculations and whatever you're doing, because that lets you show to other people that you're doing something scientific, but also to have an answer when somebody comes and questions your work, you know where to go to point them towards it. You don't have to look this up 6 years later, figure out what you did. It's right here on the paper. Okay, I use the method of McCaffrey, Quinteri, and Harkleroad. That means I need to go to my SFP handbook on this page, and if you're thinking way ahead, you might copy a piece of that those pages from the book and put them in a folder somewhere with your case notes for this one. Anyway, if we go to our case, our little room, we've got a 12-foot compartment. We'll put 10 feet for the length. We'll give it 8 feet tall and a vent width of 2 feet by 6 feet high. And then we're going to say that this is 1/2-inch gypsum board lining. So what's going on here is the spreadsheet's calculating a interior lining thermal conductivity, or it's looking that up for gypsum board essentially. We're going to use that and the thickness of the gypsum board to calculate a conductive heat transfer coefficient. We're also going to calculate the area of the vent, because the ventilation that's available to fire is important to us for flashover. And the total area of the compartment is this number, as it turns out, is also important to flashover. So essentially the size of the room is going to matter to whether you can flash it over given a certain fire or not. So if we do that, we get 3 different numbers here, right? We get 636 kilowatts, we get 1131 kilowatts, and we get 991 kilowatts. One note that immediately jumps out to me here is, I think it was Quinteri that said it first, is we don't put people in jail over a kilowatt, basically. So if I see a number like 991 kilowatts, in fire terms, we can just say that's about 1,000 kilowatts. We don't have that level of accuracy that we can start reporting numbers like 991 point something, something, something. So we're talking about ballpark figures here, just to know whether we're close or not. So already, I see that one of these here at least has a number around 636. So let's keep that in mind here. Remember earlier, we looked at this video here of the chair. And the peak for that chair from this test, I believe, was about 650 kilowatts. And we're somewhere here. So what that tells me right at the bat is already I probably know from this simple calculation and knowing the heat release rate of this chair that I probably have a big enough fire to cause a flashover in that compartment. And we can stop there, we can think about it a little more. If I go back to the original drawing, so I have my chair, I put it in a corner, I know my peak heat release rate is 650, and I've got less than that required by the spreadsheet to cause flashover. Say we add a few other factors in, like the fact that it's in a corner might cause the fire to grow more rapidly to a high heat release rate, which we'll discuss in some later classes. Basically, it makes me comfortable that I didn't need somebody to come into this room with a gallon of gasoline poured all over the place to cause flashover, that this chair should be enough. And if I am worried about some of these larger numbers here, some of the other calculation methods, I might dig into those and see what some of the assumptions are. And I'll actually find, in this case, that the method of McCaffrey, Conteri, and Harkleroad is a little bit better for a somewhat smallish room like the one we're talking about. I might not use that for a warehouse fire. For one of those, maybe I would look towards Bobrowskis or the method of Thomas. I'd have to read in these references to remember which one those were and figure that out for a fire scene. So I will say one note before we move on a little bit here. As we're doing these calculations, remember, like I said, 1 kilowatt shouldn't be the difference between someone being guilty or not, essentially. So we don't want to put too much weight in these small little numbers. So if you see a lot of numbers in tables, like with lots of decimal places behind them, then we typically in fire, we're going to need to round those. So don't carry along a lot of decimal points. We need to look at only the number of digits that are really significant to us that we're comfortable with. So basically, don't carry forward lots of small numbers and decimals. Just go ahead and round those to the nearest number. You shouldn't wind up with more decimals at the end than you put in at the beginning, essentially. Back to our problem. In this case, we're fortunate enough to be able to check our answer with some full-scale testing. We probably don't need to because we're comfortable with our spreadsheet here, but let's show this video of our scenario that we just talked about. And this is our 10 by 12 room, and there's a door right about where the video camera is. We're igniting this wingback chair. I believe there's a piece of newspaper on there that's just been lit with a lighter. So if our calculations are correct, then this chair should be enough to flash over that compartment. You'll notice we do have some wood floor underneath. In this particular case, there was a hardwood floor there, so we want to just make sure that we got that extra fuel accounted for a little bit. I believe that in this case, the wood frame behind the chair was just marking the location of a window. So as you watch this, we'll picture back at those graphs we were looking at. We've now moved past that ignition phase where the heat release rate is very, very low. And we're now in that growth phase, which is that sort of steep line that's moving up the chart. And basically as the fire grows, we're heating up all this furniture, the pieces of the chair, and that causes the fire to grow more quickly and so on. As the fire plume rises, you'll see we've got some smoke developing up at the ceiling. And all that smoke is hotter than the air around it. It's got some heat to it. And that's going to start radiating some heat back to the chair and to the walls. And that's also going to help speed things up a little bit. So we can't see right now through the thickness of the smoke, but it looks like the flames are probably about up at the ceiling and coming across. And that's the time when things really particularly start to speed up in a compartment fire, which we'll learn about throughout the course, is that when you get flames across the ceiling, you really start heating all the things that are down below the floor. If there were tables, anything on top of tables or furniture, that's when the fire starts really moving towards flashover. So I would guess, based on our earlier video that we saw, that we're at least at that 650 kilowatts here. We might be a bit higher because of the fact that we're now in a room in a corner, and that's helping to cause the energy release of the chair to be a little bit faster than if we're just sitting out in the middle of the room. So now the flame, we can definitely tell it's coming across the ceiling. You'll be able to start seeing some of the off-gassing of the wood floor, the vapors coming off, or just the solid being turned into vapor, which we can then burn. So this is very rapidly approaching flash over here. Right about now, as all those vapors start to burn and the flame comes towards the door, that's flash over there. So really, just by using our little spreadsheet quickly, and now that you have the spreadsheet, you could do that in just a few seconds. If you had a different size room, we might just change our compartment dimensions, and that would change our answer a little bit, right? So hopefully that's a tool you'll be able to use going forward. Moving along, I wanted to show on our first class a more extreme example, if you will, of the use of fire dynamics. Now this is something that I would not expect to see on a lot of fire scenes, and it requires a much greater effort than using some spreadsheets, but I'd like you throughout the class to also get a feel for what's out there and what can be available when there's a really big case that requires something. So this was out in Colorado Springs a number of years ago, back in 2009 or so, I believe. It was a big apartment complex in Colorado Springs, and there was a large fire in the winter time. And for this case, we wanted to look at using some fire dynamics to provide an independent way of looking at the fire. So can we corroborate our patterns that we're seeing on the scene? Do they agree with the fire dynamics that might be proposed by the hypotheses that we're coming up with, or were we missing something on the scene? So the analysis and testing I'm going to show you let us test out different theories, different hypotheses, to try to figure out where this fire started. Quick overview of the building. We had 5 wings all connected together. The north and northwest wing over the right side, and we had the south and southwest wing on the left side, and those were connected by the center wing. And the whole building was about 3 floors. You'll see on the drawing there were open stairs in all the wings, where I'm putting my pointer here. And those were essentially all the way open from the bottom level, which we'll call level A, up to the top level, level C, as well as these hallways were for the most part open without any doors closed separating them. So it's big open space essentially in this apartment complex. After the fire, it looks something like this. So quite a bit of damage. The roof is mostly gone over the north section and parts of the rest of the building. If we look at the damage to the top floor, we can kind of see the hallway area down the middle is very heavily damaged. The apartments, you can see through here, were not as bad. They're definitely damaged, but you see the wood studs down in the walls there don't seem to be charred too badly. As it turns out, in this case, the apartments had some pretty solid, thick wood doors, solid all the way through, that stopped the fire from penetrating into the apartments pretty well. Here's the middle level, we'll call it level B, in the hallway. And this is typical of the damage throughout most of the apartment. Had pretty severe burning. You can see on the drywall all the burn patterns here. There used to be wood paneling on these walls. You can see a little bit left down low here. But the apartments themselves on these levels were actually in quite good shape. You can see by the condition of these ceiling structural elements here that the fire probably didn't penetrate up there. It's more likely the drywall just fell off because it got wet during fire suppression. The lower level, level A, was pretty much undamaged other than a little bit of light smoke and quite a bit of water from the fire department efforts. We had 2 fatalities in this case. One was on the top floor, level C, of the north wing in this far apartment. Call that unit C19, I believe. And He looked like they found him by the door. It looked like he had probably opened the door, took a breath of some really hot gases of fire, and probably dropped right there and had quite a bit of thermal damage to that victim. The victim on the south wing in Unit C5 was a little bit different case. He did not have a ton of thermal damage from the fire. Actually had very high blood alcohol content. Looks like probably never woke up during the actual fire. So in this case, we wanted to do some analysis, not really looking at the fire patterns from the scene, but what were the other types of information we could use that would help us interpret those patterns that we see at the scene. And the things that are left to us here, we've got a lot of witness statements from a lot of different people that were in this apartment complex. And then we have our fire dynamics, which we'll be learning about in this course and which can be helpful in a lot of cases like this. So we took that information. The original plan was to use a computer fire model to investigate the movement of the fire and the smoke throughout this building. And it turned out that we needed a little bit more information than the computer model could give us. So some full-scale testing was also done to get a handle on the beginning phases of the fire growth. And that all feeds into an opinion at the end of the day. The witness statements were interesting here in that we had more than 300 statements from lots of different people, but nobody really had a good picture of the overall fire. They all just had a small little piece of what they noticed as they were being rescued from the fire department, or they were fleeing during the fire, or some of them who were on the far side of the building maybe didn't really see the fire until much later from, say, a parking lot across the street. So in this case, what was done is all the different statements were drawn out on this map of the complex. We can see the blue outline apartment buildings just indicate the units where there was nobody present on the night of the fire. The gray here shows where people reported seeing smoke, and the red is where they reported seeing flames. So what we find actually, there's a couple blips here. Turns out these ones, the one off to the left in level B and the one sort of a little to the south of the rest of the main body of fire, were people that saw stuff quite a bit later on from outside the building. So the main body of fire, which most of the witnesses reporting were on this north side, both on level B and level C. And from what they're describing, essentially we had flashover happening on level B and level C at about the same time as each other. So fire progressing on two levels at once. Some other useful information that we might want to look at is how people got out of the building. So we see on level A, we had a few people up north and even down south pulled out by the fire department, but most people simply left through their windows, which were on grade level, or went out the way they normally would. So nobody having to do anything too extreme to get out there. On level B, down on the south side, we see that most people just came out in the hallway and they exited via the door that they typically would use, whereas most of the people on the north side either had to jump out their windows or were rescued by the fire department. Level C, very similar to level B in that the south side people typically got out via their normal exits, and the north side people were jumping out windows and being rescued by the fire department. So already that's telling us something's up with that north side on level B and level C. So through that kind of analysis, we're able to already start narrowing down, okay, the fire then must have started somewhere in that north wing, and it might have been level B, and it might have been level C. So we want to try to use our fire dynamics to back out which of those levels could it have been, or, did it have to be both levels even? So we go back to some of the fire fundamentals, which you're going to be learning about over the course of this class. And in this case, we know that the open stairs would have been a really nice path for that fire to travel. So the question becomes, did that fire spread up from below, so from level B to level C, or could it have spread down from above, going from level C to level B? if we start breaking apart the movement of fire a little bit, let's just look at how fire tends to move when it is doing its normal thing. And generally it's controlled by buoyancy of the fire plume. So what that means is we have our fire, it's very hot. There are hot gases coming off the fire, and because those hot gases are less dense than the normal air around them, then they'll rise up. You know, it's like a hot air balloon, essentially. When that happens, we also induce a bit of a flow. We've got the hot air going up, and then we get this cool air coming and feeding the fire towards the bottom and from the sides. And we call that cool air coming in. That's air entraining into the fire. So the air coming in and air going up with the hot gases, and you generally get this upward movement of fire. So as a first pass, one might guess that the fire is more likely to start on level B and move upwards just from the general way that fire behaves and how buoyancy is going to make things go. But because this was a pretty good trial, and they actually were considering the death penalty at one point, the decision was made that we couldn't really stop at sort of the simple answer that fire generally moves up, so it must have started on level B. We wanted to look at, was there something about this building, any special case that would have caused it to do something else? In this case, you know, something that might have caused that would be different ventilation flow paths. Maybe there was a very strong wind blowing in and there were some doors open on the far side of the building, because this is Colorado Springs and there's often wind coming out the mountains. So there were different things we wanted to look at before sort of calling it a day and calling the fire on level B. So the first step actually wound up being doing some full-scale testing to try to get a handle on what the beginning part of this fire would have looked like. So what's going on with the fire growth right after ignition. And to do that, the best way to do it was to build out a small portion of the north wing, which was still quite large. It was something like 50 feet long and a couple stories high, as shown by this little red box here. So this is what that build out looked like in the laboratory. And you'll note a few things. Basically the hallway was built. The units on either side of the hallway were not built because those solid wood doors, which are in place here, stopped it from moving from the hallways into those units. You'll see that we've mocked up the top level, level C. We've mocked up level B here, and we've raised the whole thing up. And we did that to sort of simulate level A being below and there being some way for the air to come up from. So here's what would have been the east entrance of the north wing. You would have walked in. If you could have gone down some steps here, you'd have gone to level A. These steps to the left lead you up a flight to where level B is. And then there's another interior stair that continues up to a landing that's open to below where this window is. And then it goes upwards to level C. Moving to the inside of the structure, you'll see a number of things here. We're looking towards the stairwell from the inside hallway of level B. And we'll talk about some of these instruments as the course goes on, I think. But this here looks sort of like a rope. That is our thermocouple tree. And what it's doing is measuring temperatures at a number of different points along the way. You'll see these little tubes sticking out here on the ceiling are measuring the velocity of the air moving up and down the stairs. And you'll see throughout some small cameras here and there, which I'll show you some video of in a moment. A couple things to note. There's a lot of wood paneling in here, which was matched doing some small scale testing using samples from the actual scene. So we're putting in materials that are as close as possible to what would have been in the building, as well as the carpet samples, which were identified by some trace chemists, so we could put in representative carpet to the test. So this is just a quick little aside. The small scale test uses a cone calorimeter, and that is really the same as the instrument that I showed you that was measuring the heat release rate of that chair earlier. essentially looking at how much oxygen is consumed in the air when I'm burning a little sample. So I can compare the amount of energy in a small sample wood paneling from the scene, and I can burn a number of wood paneling samples from the store and try to find one that most closely matches what we had in the actual fire. In this case, the exemplar carpet sample was picked out, I believe it was a looped weave nylon carpet. So just back inside, you'll also notice we have some smoke detectors. These two doors here are the doors to the units at the end of the hall. So this one on the left would have corresponded to the apartment below the first victim, and then there's the apartment next door. So the first video we're going to look at is, what if we pour the gas upstairs? I should make an aside here. What I forgot to mention was that there were some gas hits found positive on the stairs leading sort of in the front door in that area and up on the stairs, at least up to the units on level B. And then the stairs up to level C were pretty well damaged. So we're looking at a scenario where there's gasoline poured, just a small amount, in front of the door to unit C19 where that victim was, and igniting that and seeing what happens. So let's watch this. So what we're going to see is the stairwell view in the upper left. In the upper right, you're going to see the unit door up on level C where we're pouring the gasoline now. I'm going to ignite that with a lighter coming in from behind the door. The lower left, you can just see a view all the way down the hallway on that top floor, as well as the lower right, which is a similar view but looking at an infrared camera. So the purpose of this test then was to see, okay, if we could light a fire here and it moves down the stairs and flashes over level B at about the same time as level C, then that might be a possible theory that could have worked in the actual fire. Now we know from our quick discussion of fire dynamics that the fire is more than likely going to move up, right? Because we're going to need to feed the fire with some air that's coming from sort of down low and it's training in. In this scenario, the likely route for that air to come is up the stairs, and that's going to force our fire not downwards, but sort of up and out away from its origin. But we're going to look at it and see if there's something about this geometry that might have changed that. And at the same time, all the data that we're collecting is something that we can feed into a computer model of a larger apartment complex, and that lets us try out different scenarios. We'll get into that in a few moments. So the first thing you'll notice, the gasoline helped us get the fire started, but it pretty quickly moves from a fire involving gasoline to a fire that's really mostly involving that wood paneling that's on the walls. And it's already starting to move a little bit down that level C corridor, but you can see here on the video nothing's moved downstairs. There's no elevated temperatures down there at the moment. No smoke detectors activating. And you can start to see why. If you look in this upper left corner where that smoke is, the layer is trying to come down, but if you see all this sort of swirling in the smoke, what that is, that's the air entraining in from below. So the air is pushing up, the cold, fresh air, to feed the fire, and it's keeping it from coming down. And now we see on the bottom two images that we've essentially, before 2 minutes are even up, caused flashover of level C, whereas level B at this point is still fine. There's no smoke down there, there's no heat, so people could be walking around on level B and be okay, whereas level C is completely engulfed. So at least as a first pass, this hypothesis that the fire started up on level C is not looking too good. The next scenario that was looked at was now a fire that started a level down. So now we're looking at a fire in front of unit B19 Also with a small amount of gasoline poured and ignited with an open flame. The camera views are very similar to the last test. Upper left, you're going to see the gas poured in front of level B, unit 19. The upper right is going to be the view up that open stair that's right next to it. You can see in the bottom left, the man pouring the gas there from the end of the hall. The bottom right is actually looking at the top floor now from the end of the hall, again with the infrared camera. So something to notice as we look at this, remember the first test we had flashover in a little under 2 minutes. As this one grows, what we're going to find happening is a lot of our heat now, instead of being sort of trapped and focused on one level, is going to start spreading around. It's already moving up the stairs, spreading up a little bit. You'll be able to see some of the heat in that infrared view in the bottom right. Right about now it's coming in. So what that does is we're now impacting a larger area with our fire, but it's going to take it a little bit longer to reach flashover because it's not focused in one spot. It's sort of spreading up through convective heat transfer. So we can see we've got fire mostly in the door still. We've got heat coming down both hallways, levels B and C. And now the flame's just starting to extend a little bit up into the stairwell. So already in the last test, we were approaching flashover right now, essentially. We're very close to it. But right now, in this test, we're a little bit behind because we're spreading that heat out, essentially. But what we do see is that we're getting similar conditions on both levels. There's still more fire on level B right now, but as you'll see in a minute here, it's going to start to progress up the stairs quite a bit. So now we're starting to get some flames across the ceiling on level B. And at the same time, all that heat is pushing things up to level C. We're sort of preheating all the wood paneling up there so that when the flames do make it up, they're going to have already some preheated fuel to work with. If you notice some sparks in the lower left, that's arcing from the light fixtures that are run at the ceiling of the hallway. So we've got a lot of fire in level B now, but it's not quite flashed over. You don't see too much preheating of the stuff that's down low. But like I talked about before, once that flame goes across the ceiling, stuff speeds up. And there it goes. Now it's come up the stairwells. We're up on level C, and we can see the heat sort of marching down both hallways. And in this case, we did get flashover of both floors right about now at essentially the same time as each other. So that makes us feel pretty good about the scenario where the fire started on level B in that north wing. And this image here is actually quite similar to what one of the responding firefighters reported as seeing when he arrived on scene. So we just look at some pictures after the test and after the fire scene. It does look fairly similar at least here. We see we have some of the wood paneling remaining in the test, a little bit more than the actual fire scene, and that's because we didn't let the test burn for more than a couple minutes, whereas the actual fire would have burned for a couple hours in there. So the testing is nice, and it backs up our fire dynamics in that we think the fire would go up essentially and not down. But there are some limitations because of the fact that we're not building the whole apartment complex. It's not the exact same thing. We're not in Colorado Springs in the wintertime. So we need to be able to talk about the effects of some of those limitations. So how do we work out what if these airflows are different when we have a whole building involved? What if the fire was limited by the oxygen available in the real fire as opposed to our testing where we had a wide open end to our hallway? What if perhaps some of the entrance doors on the far side of the building were open or closed? Would there have been some impact of wind? Or even what if the actual fire started out more slowly or more quickly because there was more or less gasoline involved, or maybe some other method of igniting it that didn't involve gasoline? Or what if there was some difference due to the wood paneling in the carpet and whatever variations there were there? So in order to address some of these, the best way to get at it in this case was to use a computer fire model. And for this case, we used Fire Dynamics Simulator created by NIST. And this is just an image of what the building looked like in the model. So how the model works, it uses what we call computational fluid dynamics, or CFD. And essentially, we're predicting the movement of all the mass, the energy, different gases and things that are moving around this three-dimensional space. And we do that by breaking up this big apartment complex into lots of small pieces. So each of these little pieces that we break it up into will be, in this case, a cube. And don't worry about the math too much here, but essentially what's happening is the computer program is tracking how much stuff is coming into each one of these little cubes every second or every time step, and how much stuff is coming out, and all the different directions and velocities and momentums of all that stuff as it moves around our space. So as an example, if we have a very square and lovely purple furnished living room here, what the computer model would do is break that into this mesh that we see here. And each one of these little squares that you see would actually be a three-dimensional, what we call grid cell. And over each of those cells, the computer is figuring out where's everything going, where is it at each point in time, essentially. So what that lets us do in this case is expand from our smaller test area. We can take that data that we have from those tests and we plug it in to the whole apartment complex, which looked something like this in the computer model. And what I'm going to do now is just show you a couple of videos from two of the runs. And what the computer model allows us to do too is test out many scenarios. So while burning it down in the laboratory 50 times would be maybe a lot of fun, it would also be highly expensive and not get us all that much information necessarily. But what we can do is do a couple of tests in the lab, get the information we need, and then we play with it in the computer model and answer all those sort of what if questions. What if the wind flow was there? What if this door was closed? What if the fire was smaller or bigger? And we could do 30, 40, 100 different computer model runs to test that out. So what we're seeing here is the 3 levels of the apartment complex. The bottom is upper left here, level A. The lower left is level B, and the lower right is level C. And you're going to see, in this case, the fire started on level C, where the smoke is moving throughout the apartment. And you see how it sort of marches from the north down to the south. And when we look at level B, the smoke first appears actually down on the south there, because it's sort of coming down those open stairs, and then it works its way back towards the north. That's just the way the airflows are moving in this space. And what we found was whether we open and close certain doors, whether we put a wind there or not, whether we change the fire size, that may change the amount of time that it takes for the fire to move around, but it pretty much always followed this pattern. So if we started up at the top level, it sort of went from north to south before going down to the next level down and working its way back up. So that's not what people were seeing during the fire. So this fire in level C, no matter what variables we changed, didn't fit what happened in real life. If we look at a similar model run, but this time we start the fire on level B here on the north side, what we see there is it pretty quickly spreads up to level C, and then both of these levels move from north down to south at about the same time. And that is consistent with what people saw during the fire. And that trend happened whether or not we changed all kinds of different variables. So that makes us feel comfortable that even by playing with lots of different things, there's a general overall sort of flow path that this fire is going to follow in this building. And it's also consistent with what we know of fire dynamics. And when we add that to all the witness statements, I think we're very comfortable in this particular case being able to say that, yes, that fire did start somewhere on level B on that north wing up in this first area here. So just to list here, there were, in this case, 25 different simulations looking at all kinds of different things. And at the end of the day, we had that fire starting at the north end of level B. It was not consistent with a fire starting at level C or in any other wing, for that matter, of a different floor. In this case, it turns out that the girlfriend of the main suspect did live up at that north end of level B, and that was the motivation for starting the fire here. And it wound up going to court a few years back and getting a conviction of the suspect for starting that fire there up on level B. A couple lessons learned in this case for those of you who are working large fire scenes and maybe are on the witness interview side of things at times is that really some questions got better information than others from those witnesses. Particularly things like asking a witness where we saw fire might not be really useful because some people might consider smoke fire, some people might consider flames fire, and unless you can differentiate between the two with them, you don't get as much information as you might like to have. Also, where were the people when they saw the smoke and their flames? Maybe they were in their apartment, but maybe they were at the 7-Eleven across the street because they'd already evacuated. Asking if the fire department was already there or not when they saw this helps us to establish a timeline for their statement. Asking them what route they took to get out of the building helped to figure out was there something going on that prevented them from taking their normal exit route. And then one that was also really nice was asking what were the first 5 things they did when they became aware of the fire. And that's where some of the interesting information came out about people that maybe walked out and then they realized that they forgot their purse, so they went back in and they passed a couple areas of interest and saw different things. And you might not get that kind of information if you don't ask these sort of leading questions for them. But we'll save the witness statements for another day. That wraps up for this week our examples in our fire dynamics lecture, but I just wanted to take just a few moments, since this is our first class, to talk about some of the expectations for the homework assignments that we'll be having. The first is a discussion board assignment, and that's what we're going to have this week. There's going to be one of these assigned every other week. Basically, there'll be some sort of paper to read or a video to watch or some other type of material to review, and then we're going to have a discussion about that material on the class website. Something important to note, this is not a public forum. Nobody's going to be able to come on and read this and archive it. If they're not part of the class, then there's no access to it. So this is sort of a place where we can debate things, and if you want to put a little thing in your signature block to tell people that this is academic and you're doing it just in the spirit of debate, then you're welcome to do whatever you like there. But essentially, we want to have a good conversation about some of these topics. And your participation in that discussion is actually going to count for about 22% of your final grade. So please do go online and contribute there. And that'll be every couple of weeks. On the alternating weeks, when we're not doing the discussion board assignments, I will be assigning some what I'm going to call the problem assignment. So this is going to be usually some sort of math problem set involved with fire dynamics, typically something related to a fire scene, and using maybe spreadsheets or just doing some math by hand if you prefer. And the key here is I'd really like you to show the work that you've done. If you use a spreadsheet, then you can submit that as your answer. If you're doing it out by hand, then you can just scan that and submit that. And what I'd really like people to do is provide references of the different equations, things that you're using, whether that be a page in your textbook. You don't have to print it out, but just write down where you got it from, essentially. And that's going to also count for about 20% or so of your final grade. And you'll typically have 2 weeks to complete those. We will every week have a short online quiz, and that's typically going to be sort of multiple choice, short answers, and that's just to show that you're getting a handle on the material as we go through week by week, so I can keep track of if we're all watching the lectures and whether I need to cover certain topics in more detail. And that we're basically going to give you 1 week to complete, and we'll count towards about 20% or 22% of your final grade. The term paper, you may have seen in the syllabus, or maybe this is your first time hearing about it, but there will be a paper that you will need to write before the end of the class. The paper itself won't be due until the very beginning of December, but I would appreciate if you could let me know by September 1st what's the topic that you would like to write about. And this can be anything with a fire dynamic spin on it. If you are working on a research project of some sort already, then this could be based on that same topic, and you could actually use this as a chance to get a start on writing up some of the research and literature review for your research that you may be doing. Basically, we're looking at something that's going to be several pages, probably more than 5 and less than 12, say, but whatever it needs to be to just discuss a topic in fire science or fire investigation, put a little bit of a fire dynamic spin on it, and style it along the lines of something that you might read in the IAAI journal. And in fact, if you would like to submit your paper to the IAAI journal after the class, I'd be happy to help you format that or work on it a little bit if you wanted to tweak it before you submit that. But that's not going to be required for the class. It will, however, be required that you write one, and that will count as about 22% of the final grade. There will be a final exam. I believe it's the first week in December. It will contain a number of problems that are very similar to those that are in your textbook, as well as the weekly problem assignments that I'm going to hand out. So it will be open book. You can use whatever Excel computer programs, books, anything you would like to complete it, as long as you do so by yourself. And you'll have 1 week to complete the final exam for about 14% of your final grade. And please do remember, because we're teaching this for college credit, it will be expected that you get a B or better, which would be an A. So you don't want to aim for a C in this class. So these assignments will definitely count. You want to complete them all to the best of your ability. I will, from time to time, offer some extra credit that will help add a few points here and there if you are willing to do that. So one last note for this week, Week number 1, our first discussion board assignment will be for you to watch this 2020 video segment, which you can access on Hulu at the link below. I will also provide a link on the course website. This is about a 40-minute long video that goes into some interesting areas in fire science and some fire litigation. So I encourage you to watch that, and I'm going to post some sort of topics on the discussion board that I'd like you to discuss over the course of the next couple weeks.